But what I'm going to talk about today is, in fact, as Felix calls it very correctly, it's a tutorial style talk. So do not expect so much in terms of scientific new content in the sense that hasn't been there before, but more of an overview of what we all should be doing, but most of us don't do for various reasons. And we will get to the reasons very soon, but the idea is really to talk about how to report performance numbers. So this comes with a bunch of disclaimers at the beginning, and in fact that, as I just mentioned, this is an experience talk, so this is really not a scientific talk. I hope you will not be disappointed, but I believe many of you will be learning something during that talk. At least I would have learned something if I would have been in that talk a year ago. So don't expect a novel insight, but again, I think each of us can learn something, and I want to make this very interactive. So if you have any questions, any concerns, any complaints, especially if you see something that doesn't make any sense, immediately stop me and I will try to explain it. If I can't explain it, then you won. Okay, so also do not be offended. Actually, all of the examples in this particular talk come from real scientific papers, all of them. I decided to remove the names after giving this talk a couple of times for various reasons. If you find yourself, then be concerned, but be not offended, please. Okay? Good. Also, a little bit exaggeration is, of course, here because the talk shall be entertaining. This is one of the most important features of this talk. Okay, so let me actually introduce you one of the major players in this talk. So this is Garth. This is Garth the Garlic. He is a young student, and he actually thinks he knows how to report performance. He's been writing scientific codes for his life, his very short life, and he's doing high-performance computing. So, and really what we want to do here in high-performance computing is we want to really see this as a science. Right, so this is our fundamental attempt to do this. So really the computing as a science, and of course high performance computing, the middle word is performance, so we want to see performance as a science. And of course if we do anything with the science, we need to reproduce the experiments, we need to make them reproducible. But we will get to reproducibility in a couple of minutes because I have a pretty extreme opinion on this. But of course, when you report performance, and again, we want to see it as a science, so you want to do it scientifically accurate, you have to ask yourself certain questions. So for example, how many iterations do I have to run per measurement? How many measurements should I run? And all of these questions here, once I have all the data, how do I summarize it into a single number that I plug into my paper and say, hey, I'm better than the other guy, which is what you usually do. How do I compare performance? Exactly, if I want to say, hey, I'm better than the other guy, how do I do this? And how do I measure time in parallel systems? So all of these questions are open. And interestingly, we answer these questions, of course, for each of the papers we write. We choose the number of iterations to measure. We choose how many measurements we perform. We choose how to summarize the data. But there is very little structured approach how to actually do this, and very little education, unfortunately, how we should really be doing this. So the state of the art is somewhat not so great. So let me start with an anecdote. So in fact, this is a reaction to this particular paper. So I published this paper at Supercomputing last year. And this is a state of the practice paper, really criticizing the community a little bit. And the first reply I got was criticism of myself. I love that. So in fact, what happened is immediately, basically, after I put this paper on my webpage, somebody told me, like, look, you wrote this paper in 2006. Okay, yes, 9 years ago, I was a young student and I didn't quite understand everything I understand today. And in fact, I wrote this paper on non-blocking collectives, blah, blah, blah. If you know me, you know that this is my background. So in this paper, there's one plot. That's this particular plot. This plot is really bad. Right? If any of my students would be producing this plot today, I would not let him publish that paper. So, and you can now think about what's wrong with this plot, and we could talk about this for at least 20 minutes because there's so much wrong with this plot that we can really entertain quite a bit. The major problem with this plot is that it plots a speedup over a number of CPUs and doesn't actually say anything how performant the code is. Right? It just compares a blocking version to a non-blocking version. It just claims out of nowhere that the non-blocking version is, of course, faster than the blocking version, because at that time, that was exactly what my research was about. So great, the paper got accepted. I'm happy. But let's now look a little bit into details here. So the finding of this paper, and the finding is still true, so it's not invalidating the result, it's just that it's not really demonstrating the result very well. The finding is, if you carefully tune these non-blocking collectives, they can speed up a three-dimensional solver, right? With this, of course, in order to foster reproducibility, at that time, I published the full code. Right? So you basically can go, and you can still go to my webpage and download this code. So the input set was an 800 cube domain, which is about 4 GB of data in a distributed array. So we ran one process per node, blah, blah, blah. And this really old Optron, actually even at that time it was already old, like very old in fact. And so we observed some superlinear speedup, as you can see here. 96 processes kind of give you more than 100, a little bit more than 100 speedup. So there's like 5% superlinear speedup, which today, as we all know, really means that the serial code was just not well tuned. Right? This wouldn't have happened if the serial code was well tuned. Sure, but we didn't really care about the serial code at this time because we really wanted to show that the non-blocking collectives are better than the blocking collectives. Right? Okay, so then 9 years later, somebody in fact attempted to reproduce this result. This is great. And they wrote a paper about it. Wonderful. And immediately I got a copy, as I mentioned, as a reply to my paper. Like, look, your research is not maybe not reproducible. So, and they compared it on 2 different systems. So system A and system B. So this is the system that I used 9 years ago. And so here is a 28 node quad-core Xeon system and a 4-node 24-core Optron system. Right? And they state in this paper, neither the experiment in system A or B, this is anonymized, by the way, it's locations, but I don't want you to know exactly what this is, reproduce the results presented in the original paper, where the usage of the NBC library resulted in performance gain of practically all node counts, reaching superlinear speedup of for 96 cores. So basically they say, okay, we cannot reproduce the result. If you look at this graph, you will in fact see, and maybe we don't have enough time to in fact look at this graph in great detail, but what you will observe, well, actually the claim is they actually confirmed the major claim of this paper. Because you can see here, just for this example here, the blocking version MPitch is slower than, I mean this is time here, right, than the non-blocking version. The non-blocking version is faster, beginning from basically 1 node here, right? So here it's basically the same, which is the same in this graph. So in fact, it's very interesting that they reproduced the result correctly, but they couldn't see the superlinear speedup. Does anybody have a suspicion why they didn't observe the superlinear speedup running exactly the same code on a system 9 years younger? Yes? You might have a different compiler, or your whole input set may fit in some cache layer or something like this, right? So of course, it's a completely different system. You will not see the same results. So this is just a case study or an example, first showing you that I make mistakes as well, of course, hopefully. And second, show you that performance reproducibility is actually not easy. It's extremely hard to reproduce any performance measurement. So, and now, of course, this is one example, but what we did is kind of a study looking across a larger number of conference papers, how this looks, how the state of the art in the field looks like. So we took what I believe are the top conferences in high performance computing, or at least a sample of them, HPDC, PPOP, and supercomputing across 5 years. We took 10 random papers from each conference, right? So this covers about 10 to 50% of the population to give you all the information you need. And so a total of 120 papers, right? Unfortunately, 25 of them did not care in any case about performance, right? So we had a total of 95 valid performance papers. And then a very clever student of mine who decided to move on to industry created this table. So this table is the anonymized conference version, because again, you don't want to get into trouble when you publish these things. So, but of course, it comes from this sample, right? You can now do the permutations if you want. So the anonymized conference versions, and then different metrics for experimental design. So hardware specification, software configuration, and this is all relatively boring because this is really just the section of that you typically should have in your paper that says, well, my experimental design is X, or experimental settings. So it turns out that this is not great. What's more important is this section down here, and this is what I will basically spend most of the time of the talk on. The main results of this study, when you look at this table long enough, you will actually find that most papers report details about the hardware, but they really fail to give you the software environment. And if you've run anything on a supercomputer across different updates of different software versions, you will realize that the performance is quite different. So if you want to reproduce anything, you need to give the whole, the whole story, basically. And then what I'm claiming based on these results is that the average paper in HPC is really hard to interpret. What it means is I cannot really understand where the observed effects come from. Or in other words, if you present me your paper, I can attack your paper until you cannot argue your way out of it, right? Until I can say, look, there is a problem in your measurements, and it could have been something that you're measuring that's just observed by chance, for example. I can argue this for most of the papers. So, which is basically the third case as well. There's no the third case is actually depressing in the sense that there's no statistically significant evidence for improvement in this over the years, right? Remember, the table goes over the years, and I would expect that the experimental methodology in high-performance computing gets better over the years. It does not. Not at all, actually. Sometimes it goes down, but it's all in the noise. Okay, so and then that gets us to the main thesis, and the main thesis is, in fact, that I believe performance numbers in high-performance computing are impossible to reproduce in any practical setting anymore. Right? This is the most kind of aggressive statement I'm going to make in this talk. So this really means that, look, I cannot repeat an experiment that you have run before, because this computer will not be available at the time when you run it. So the conclusion from this is basically that you really want to give the scientist who reads your paper enough information about the content of your paper or the methodology that he can interpret your results. So there's reproducibility, which means I want to reproduce a result one-to-one, and there's interpretability, which means I want to understand how you got to this result. Typically in science, you want to teach something to make somebody understand, right? Extremely important. Okay, so now let me get to the point. So we all exactly know all of these things. We all have seen many examples like this. Oh, so basically, this is the second player in our game. So this is Eddie, Eddie the eggplant, and Eddie is the person, is the good guy, the person who will tell Garth how to do it right. Right. So just to make this a little bit more entertaining, but we've all seen examples of Eddie. So, for example, David Bailey published his overview of 12 ways to fool the masses in '91. Then there is the shocking that I really find very shocking. This is very interesting if you want to look at it, but I will have the main contents in this talk. How did this get published? Really funny presentation. And then, of course, our friends from Germany have been extending this. So we all know these examples where people essentially tell us what other people are doing wrong in their measurements. And this is great. This is extremely great if you're a reviewer, right? Because if I'm reviewing a paper, there's nothing better to essentially say, well, you are violating rule number 11 of Bailey's rules, or any of these rules, and thus I can reject your paper and I don't need to think about this anymore. So this is very good, but the problem is for young students, or even for researchers, it's not a really good idea to just have all these counterexamples. So that's what we try to do, is we try to provide a set of constructive rules, not destructive, not saying what's wrong, but saying how to do it right. Right, in this particular paper. And I will go through these 12 rules in some detail. So, however, this set is by no way complete, and probably will never be, but I encourage all of you to try to contribute to this set, really like the 12 Berkeley dwarfs in this sense, or 14, or in the number keeps changing because exactly of contributions. But here, we should have rules for reporting performance numbers in our general audience, or in our general field. Okay, so the most common mistake we've already seen, speedup plots. And this is really horrible in this sense. Because the speedup plot can show you anything. It's a relative plot of performance performance system A to performance system B. So I can basically take a really bad performance system A and improve it by 10,000% and then be happy, right? Unfortunately, this is really old, since 1988, when we've not gotten rid of this. Right? So this is incredibly surprising. So out of these 95 papers that we looked at, 39 papers reported speedups, but 15 of them did not report the base performance. So basically, you have no idea at all if the base case is even reasonable, or if it takes years to run. Right? And in fact, this is now rediscovered in the big data field, where everybody is only talking about scalability and not really about what's the actual performance of your code. And this is very funny if you try to reconstruct any of these data mining examples on an MPI system, and so you get easily a speedup of 10 to 100 over Hadoop, at least the Hadoop version that writes it to disk. And this is, of course, rather problematic. So the best example I know is this paper. It's in fact very funny. So you should totally look at this. So the idea was that Frank McSherry, who was at ETH, he has this nice laptop here. And this nice laptop he was able to beat, I believe, a 500 node cluster on a 500 node Amazon cluster with a graph calculation, right? So solving the same problem faster on this little $200 laptop, just because they cared about scalability. So they showed, oh great, it scales to 500 nodes, but actually it solves the problem 1,000 times faster than, sorry, 1,000 times slower than, I don't know, a reasonable desktop machine. But nobody cares about this in some fields, right? They start to care, and this is rather problematic. And of course, I have made the same mistake, and many of us make these mistakes. So please do not give speedup plots without a base case, right? It's very important. Okay, so this is basically rule number 1, and I don't want to read these rules to you. I want to give you the intuition of what these rules mean. And so basically, a simple generalization of this rule is very interesting as well, that you should never ever report a ratio without a fixed number. Right? If you have any ratio in your code, you must report the fixed number with the ratio. Right? Otherwise, your ratio is pretty valueless. So for example, if I'm telling you, well, it's half price, right? But what does this mean? Right? Half price of what? Right? It could be really expensive, and then half price is still too expensive for me. So this is just a real-world example. Okay, so now let's look at a different example that illustrates rule number 2. So here we have this guy here. He wrote a new compiler. By the way, many of these flaws are very visible in compiler conferences. So Garth wrote a new compiler, and he looks at 3 different benchmarks: NAS, CG, LU, and EP. Right? Many of you know these benchmarks as the NAS benchmark results. You have ICC, the Intel compiler, the LVM compiler, and then Garth's cool new compiler. You can see, well, of course, Garth CC always gets a higher performance here in gigaflops, so the higher the better. Great. But now if this guy asks, well, how do you perform for FT and BT? Because you know that NAS has more benchmarks, and they say, well, as many students would sometimes say, well, you know, my compiler seg faults for this other case and is much slower for this BT benchmark, but you know, BT doesn't matter anyway, so I don't need to report it. That's of course, it's not a good idea. So what do we actually need to do here? And this is a very trivial rule. Basically, you really need to show all your results you have, right? So trivial, let me skip this. This is just for completeness. But now comes something less trivial, but it's, yes?
So you will now say that we should report for all system resources and all for all available benchmarks, but isn't that too expensive?
Well,
How do you use that?
of course.
Cost decision to a subset.
Well, if you cannot cover the whole set, then you need to have a good reason why you choose the subset. So you could, for example, say, I do a random sample of this subset, right? Then there is no bias. But you must avoid at least the bias. And we will get to the bias question in a couple of slides. So it's a good point. I mean, you can reduce your set, but you must do it bias-free. The only bias-free method that I know is random sampling. Okay, but now say, well, okay, yes? Oh yes, I will do that. I apologize. Okay, okay, very good. So now let's assume we now add this BT benchmark and just forget about FT because it's seg faults. We add this BT benchmark. It's 20% slower, and now you can say, well, if I add 20 and 20 and 20 and minus 20 and divide it by 4, then I'm only 10% slower. Right? Of course, I hope that most of you know that this is not legal. Because it really makes no sense to use the arithmetic mean on ratios, right? So I hope most of you know. I see some faces that are kind of nodding, and then I assume that all of you who know, they will immediately have this reaction. Well, of course, for ratios you use the geometric mean, right? This is the usual reaction. Unfortunately, the geometric mean has absolutely no meaning. So you can use it. The only guarantee you get, it's kind of smaller than the arithmetic mean. So here it's 8% and not 10%. But it really has a very limited meaning. And if you claim you know the meaning, then we should talk about it. Because it is in fact interesting, the interpretation. You can argue a long time about this. So this is not really clear. Okay, but if you actually consider the real runtime, right? And this is now a real runtime of these benchmarks in absolute time, then you will find that this runs uber proportionally long in the whole benchmark suite, and thus the overall performance is much lower, right, at the end. Okay, so this gives us 2 rules, which basically says that you should use the arithmetic mean only for summarizing costs. So what's a cost? A cost is something that you have a direct relationship, a direct linear relationship to, right? So energy, money, time, these are costs, right? And you use the harmonic mean, which I didn't mention, for summarizing rates. So a rate is, for example, watts, right? Or I don't know, speed, or something like this. Gigaflops, for example, is a rate. then you should really avoid summarizing ratios at all. Right? So never try to summarize ratios. And this is the problem. Many papers do this, but they don't, in fact, motivate this well why they do this. What you can do to summarize ratios is you can summarize the base rates instead, or the actual costs. Right? So if you look at our statistics again, 51 papers use means, but only 4 of them say which mean they used. Right? It's unclear if they used the arithmetic mean or the geometric mean. If we assume that they used the arithmetic mean, which is the more well-known one, right, then many of these papers will be wrong, right? Or the mean will be incorrect. And so actually a single paper correctly specifies the use of harmonic mean out of these 95, right? Good. And then there are 2 use the geometric mean without reason, and even worse, some of them actually kind of brag by using the geometric means. Like, oh, we used the well-known geometric mean to summarize ratios, which really makes not much sense. So in fact, if you look at Nelson's report, he will name names. So there will be references in that report pointing to particular papers at top class conferences like PLDI and CGO, which basically for some papers even change the result of the overall experiment. I mean the interpretation. And this is rather problematic. The only thing we can say for sure, and this is an interesting proof, the harmonic mean is always smaller than the geometric mean, which is always smaller than than the arithmetic mean. This is the only thing we can say for sure about the geometric mean. It's somewhere between harmonic and arithmetic. The harmonic has a clear, straightforward interpretation. The arithmetic has a clear, straightforward interpretation. The geometric is interesting. Let's put it this way. Okay, cool. So now let's say Garth is now a network engineer, and he measured latency on a particular system. So this Pitts-Dora system, this is all real data now. Actually, the previous ones was also real data from papers. But this I measured myself. So real system, Pitts-Dora, 1.77 microsecond is the latency of that system, right? So to send a message back and forth. Okay, cool. Now the question is, how did you actually measure this, right? So imagine some of your students comes and tells you, I measured the latency. And then he comes back and tells, of course, I have done 1 million measurements. So out of these million, it must be right, because if I'm having that many measurements, that's definitely the correct result. Okay, so now the question is, well, why do you think so? Can I see the data? If you look at the data, you will get this scatter plot. So basically these 1.77 microseconds down here where it's all that black, but sometimes it takes 1.2 milliseconds to transmit a message, right? So it's just statistical variation, and you may now say, well, this is not that bad. I mean, this is just, we average it out, so no problem, right? We can even remove outliers. Okay, we will see later. This is actually an interesting example that will go on. But of course, one of the basic rules that's just so basic that most people forget about it, if you report a measurement value that is non-deterministic, you need to say so, right? So basically, all performance measurements are non-deterministic. I've never ever measured a performance twice with a high enough resolution and gotten the same result. All of them are non-deterministic. So you must say that they're non-deterministic, and then you must report some kind of statistical evidence of how good your measurement is. Right? So confidence intervals is one evidence. And I don't have enough time to introduce the statistical background, but it's all in the paper. If you want to read the paper, it's down here. It's all explained at length how to actually do all the statistics parametrically and non-parametrically, but we'll get to this. So unfortunately, most papers report non-deterministic measurements, and only 15 out of the 95 report some measure of variance. It basically says, well, measure of variance means if I repeat my experiment, how close will I get to the reported value that I'm telling you? Right? So if you do not report a measure of variance, I can basically tell you you could have measured something completely by chance. Right? You can give me no evidence. And only 2 report confidence intervals, and both of them report the wrong confidence interval. So we'll get to this in a minute. So essentially all of them are wrong. Right? All of the 95. There's no single paper who does this right. So the confidence intervals is very interesting. They also allow you to compute the number of required measurements. And we can talk about this offline or in the question session later how this exactly works, but I just want to give you the right things to look for. So actually, most people then complain and say, well, if I plot all my graph with confidence intervals, I will have all these confidence bands, and it takes so much space in my diagrams, and it's really complicated, and I don't have enough pixels on my screen to plot this all. Well, you can always, almost always, add the sentence like this. You can just say, look, we measured until the 99 or 95% confidence interval was within some percentage of our reported mean. So you always say, I report the mean or the median. We'll get to this. And I measured until my data was close enough. So this implies that your variance is small enough that actually the data, the number you report, is reasonable, right? Without this, your number could be completely random, right? Okay, good. So, but then this guy now is smart. Of course, he's a smart student. He knows how to open a statistics textbook, and he knows how to read about confidence intervals. And now he says, well, my confidence interval is 1.765 to 1.775. My average is 1.7, remember. So minus 0.05 and plus 0.05. And now there comes the question from this the person who knows, right? Did you assume normality? And then, of course, the immediate reaction from the student would be, well, of course, I used the central limit theorem and normalized my data by subsumming sets of size 100. Okay, cool. Who knows the central limit theorem? Okay. Okay, so the central limit theorem basically says is if you add an unlimited number of random variables, you will be normally distributed. It's asymptotic, right? So there's no limit to it. Okay, so but now let's actually say, and this is the basis of many statistics textbooks, right? Because I can go into more details, but let's skip the details. But actually, if you look at the data, and this is exactly the same data that we looked at before, the scatter plot, right? So there's lots of points, but now plotted in a different way. This is now a density plot, which basically has the latency here and the observational density here. So basically it says that most of the measurements are somewhere here at the 1.7 probably here, but some measurements are even up to 6, right? So this is just the integral. Okay, if you now take the original data and look at this, you will see it's not normally distributed because most of you know that there is this bell curve, which this should look like if it was normally distributed. So bell curve looks like this, right? So you've all seen this, I'm pretty sure. So this is not a bell curve. Pretty clear. So now if we take the log norm, which is a statistical measure, this is still not a bell curve. Doesn't get better. If we now subsum this k equals 100, so we sum up blocks of 100, you see it becomes more like a bell curve. If we do this for 1000, it becomes more like a bell curve. But actually, these curves don't really matter. If you really want to do rigorous statistics to test for normality, you have to look at these QQ plots. So quantile plots. They have to lie on a line, and you see they're not lying on a line here. So it's rather problematic, even with subsampling 1000. So, okay, in case you're not a statistician and you didn't understand most of what I said, remember that you cannot assume normality of your data unless you prove it. The problem is that I have never observed performance data that is normal. What does normality mean? Normality means my data is centered around an expected value, and the probability to get less than that value or more than that value is equal, which means, translated to computer terms, if I'm measuring a time, the probability that my code runs faster is equal to the probability that my code runs slower. Of course, if I had such a computer, it would be great, but it's not. It usually runs slower, right? So this is why most of these curves are skewed to the right, right? Because that's slower, right? Okay. So in fact, I've never observed any normal data in practice on performance measurements because your computer system usually makes it slower, not faster, right? It's pretty obvious. Okay. So so this guy now has a problem, but now he's actually smart, as I mentioned. This guy is not stupid. So now he completes the real confidence interval. He computes it from 1.6 to 1.9, and he uses a technique that's called nonparametric statistics, which basically means that we are not assuming normality. Right? We're not assuming any distribution of the data because you can't, because you don't know your distribution of your data. It just comes out of your system, right? And you do the statistics on that without the assumption of the distribution, which is called non-parametric in statistical settings. Okay, so this gets us to a slightly more complicated rule number 6. So you may not assume normality of your connected data. Just assume. The 2 confidence interval examples that were reported in these papers, they assumed normality. And basically, well, they could be arbitrarily far off depending on their distribution of their actual measured values. So they mean right, but in fact, they don't say anything, right? It could and we will see even worse examples. I will have worse examples where the confidence interval really goes through the roof. And so you have to apply something called diagnostic checking, and that's basically looking at these QQ plots, right? Okay. So the intuition here is really that you will not have a normal distribution because most events will slow down performance, as I just mentioned. This gives you right heavy-tailed distributions. And even worse, you must understand that the central limit theorem, which many learn in basic school, only applies asymptotically, right? If you sum up an infinite series of these measurements, you will get to normality, but nobody measures infinitely often. And so then there are some papers and textbooks that say, hey, if you do 30 to 40 samples, it's good enough. right? And it's not for many examples. Okay, so here there's a problem. But now let's look at some real data. So this is in fact an example for nonparametric statistics. So real data, this was data, LINPACK data, collected from the Pitts-Stein system. So it's the Swiss national supercomputer system. It's sometimes called the biggest computer in Europe, at least in terms of LINPACK score, it is right now the fastest. So we have completion time here, and density here. So on a small subset of the nodes, in fact. It's not the whole computer, obviously, because it doesn't just have 77 teraflops, right? So in case you didn't get that. So you see, we measured it a couple of thousand times, and this is a density plot. So we see here, this is a histogram, these bars, and this guy here is the density. And we see most of the time it takes about 280, 285 seconds, but sometimes it takes 340 seconds. Right? So this is a huge variance in the in these teraflop numbers. In fact, what you do for LINPACK is statistically very rigorous, because for your top 500 list, you just report this. You forget about everything here. It's just like, the fastest I've observed is this, and so my computer can do that, right? What you may be interested in is probably some kind of mean. But if you look at this, if you just take all the data and average it, you will get this mean. But this mean is in fact not representative of your data. This is not where the majority of your data points lie in the density plot. Right? This is one example where you see that the assumption of the mean, which actually assumes a normal distribution somehow, at least a symmetric distribution, not necessarily normal, right, can be wrong, because this is again skewed to the right. If you take the median, you will have a higher chance, no guarantee, but you will have a higher chance of being at the true center of mass, as you will see here. Okay, so this is just an example of how to do nonparametric statistics. And in fact, if you know what a median is, you know what nonparametric statistics are. So what is a median? A median is very simple. I mean, a mean, you know, you sum all the values and divide it by the number of values. A median is you sort all the values and take the middle one. If you have two middle ones, because you have an even number of values, you take the average of the two in the middle, right? So this is what the median is. And you can now define, if you don't take the middle one, but the quarter and the 75th percent one, then you get percentiles of your data, which gives you even more insight, as I'll discuss in a couple of minutes. But okay, so now we realized, okay, there are non-deterministic measurements. Let's get back to the compiler example from earlier. So here, Garth CC again, and now Eddie realizes that Garth may not know what he's actually doing. And let's just look at the data where he reported this 20% improvement. So in fact, this is another way of plotting this data. So here we have lots of measurements. So here's ICC and here's Garth CC, and here's the execution time. So what we do, we show all the data, not just the one value. Before we showed simply this, and of course there's a 20% difference between the two. But we couldn't actually see all the other measurements, right? So this is a so-called box plot, and many of you may know it, and let me just quickly summarize it. This is the median of the box plot, like the middle value. And the most significant pieces here are these guys. This is the lower 25th percentile, which means if you sort all the data, you go to a quarter, and that's the value. This is the 75th percentile. Again, if you sort all the data, you go to 3/4, and that's the value. This gives you a nice idea of the spread of the data, right? But what's more important are these notches. So what these notches are, and these are most helpful. This is in fact a 95% confidence interval. So this means that the 95% confidence interval is here and here. For this ICC, and for Garth CC, it's here and here. And there's a very nice immediate test you can apply to your data if the confidence intervals overlap. Right, the two 95% confidence intervals, which you can see in this plot, by the way. R generates you this plot in like 10 seconds. Then your your result is basically not statistically significant. Right? So you can basically say, well, there is no statistically significant difference, so this 20% reported speedup is total nonsense, because it may have been observed by chance. Right? So keep this in mind. If you do anything with non-deterministic data, you need to look at the distribution and at the confidence intervals. And when you compare two different values, you need to make sure that the difference is actually statistically significantly different. Usually this is extremely simple. Right? So don't get scared. This is very, very, very simple. In most of the cases, you just have to do it. But now let's get back to some more complicated cases. So what if your distribution is not simple? So this is the same result we've seen before. So this is the latency of Pitts-Dora. Right? We talked about this. So here, this is the latency ranging from 1.5 microseconds to 2 point something microseconds. So as we mentioned, the median is somewhere at 1.7, but the average is somewhere at 1.77, as Garth reported before, right? But now, of course, if you look at the density plot, you see this is really odd, right? So most of the results are in fact at 1.61 microseconds. Then there are some at 1.9. So why is that? That's a Cray XC system. Does anybody have an idea why this happened? It's a very interesting system. So the Cray XC system is this Cray Dragonfly machine, and it has alternative paths. And guess what? It does adaptive routing. So sometimes a message is routed along the short path. Some messages are routed along the longer path. If you're now giving me the average, you will basically give me a message that I will never observe. Right? Because it's either short or long and distributed around this. The median as well as the mean is completely pointless in this case, right? Because I will never see the median or the mean in practice. How would you detect this in your data? This is tricky, right? Because if you just compute the arithmetic mean, you will not see it at all. Right? You will just report the 1.77 microseconds. You think you're happy, you think you did the right thing, but you completely screwed up, basically. If you do the median, and even worse, if you assume normality of this data, the confidence interval will look very nice. And so you're double screwed. Because you think you did it right, you think you did the CI, and the CI looks good. So basically you report total nonsense, but you think you did it right. If you do the median, fortunately, you will get a wider CI. So here you could have seen, well, okay, my CI is very wide. And you know what you typically do if the CI is wide? You try to measure more, because you hope that you will gather more data around this median. If you keep measuring more, the median will not go down in this example. It will just stay like this. It will stay like a rock. And this gives you an indication that there is something screwy going on with the distribution, right? If the median if the confidence interval does not closen up with more measurements, then you have a problem in your distribution. And then you should look at these distribution plots, right? So in this case, for example, it's a different system, Pilatus. It's an InfiniBand system. InfiniBand does not have adaptive routing. At least that system does not. And so we see a pretty clear distribution, even though I can't explain this one. It's kind of weird. It's sometimes it's really fast, but very rarely. Most of the time it's kind of slowish. And then it has this interesting flank. So again, density plot. Here the median is better and the arithmetic mean is also okay-ish. But remember, so now the question is, what if you get the task, compare these two systems? Which system is faster? And you're like, well, you know, some of the time that guy is faster, but some of the time that guy is slower. So how do you now visualize this? And this is now advanced statistics. So I can't simply explain this, but again, read the paper, and all the references to textbooks and other explanatory papers are in this paper. So there are so-called quantile regression plots. So let me give you the intuition of what a quantile regression is. So a quantile, as we discussed, is basically you sort all your data, and then you look at the rank of the data, like 10%, 20%, 30%, 40%. It's called a quantile. Right? You look how much is in that data. You can think of this as the integral over this curve. Right? So this is kind of the quantiles, because this is your probability distribution, and the quantiles is just the mass in this function. So here, what you will actually observe, and this is relatively easy to read, this guy here, this is the Pitts-Dora system, and what this means, it starts at so the point first quantile is kind of at 1.6, so which means 10% of the data, only 10% of the data is faster than 1.6. And then it goes up. It goes until the 50th quantile, which ends up at the 50th quantile is here at 1.7 something, because the 50th quantile is the median, right? If you understand the quantile, but I understand this is kind of fast, but I don't have much time, but it's really cool. And then you see that actually it goes slowly because it scans this curve. And then when it gets here, for beginning from 1.68 to 1.8 something, it goes quickly up. Here 1.68, and then it quickly jumps up because there's basically no data in this area. Then it jumps up, and then it goes further up because now it scans this part. Okay, so if you now compare these two systems, you can do the quantile regression plot for this guy, which looks like this, and then for Pilatus, which is just the difference. And you can see that for the 50th quantile, that thing is about 0.2 seconds slower. But then, actually, in the last quantile, it gets faster. Right? This is basically what you observe if you look long enough at these plots. It's just a better way to plot it. Right? And now you can make interesting observations. You can make the observation, for example, that Pilatus is better for latency critical workloads where you care about the worst case performance, but Dora is expected to be faster. So which means in the worst case, that guy is better, but in the average case, this guy is better. Right? So keep that in mind. But this is, again, rather complex, and this is rule number 8. But basically, rule number 8 is relatively simple in the sense that if you use a measure of central tendency, which is a median or an average as a measure of central tendency, then you must understand if this is even useful to report this measure. Because remember, in this case, it's not useful to report a measure of central tendency. Right? I told you some tricks how to do this in practice. If you want to know more, there's a wonderful paper why you should care about quantile regression at SIG-Arch. So it basically shows how the Linux kernel developers made a lot of mistakes while analyzing one scheduler versus another one. And it's a very impressive result, basically coming up, again, turning a result completely upside down because they didn't know about quantile regression. Was it a question or? No, okay, good. So now one of the interesting questions that often comes up when I talk to especially my students is how many measurements do we need? Because sometimes measurements can be very expensive, right? But of course you need a given number of measurements to reach a certain confidence in your statistical result. I mean, if you only have one measurement, you basically have zero confidence in anything because you could have measured something completely random. If you have 2 measurements, you have a little bit higher confidence. If you have 3 measurements, you have higher, and so on. Right? Usually, if you have a central tendency in your data, the more you measure, the more you will get towards the central tendency. It's not fully correct statistically, but most of the time. But the question is now, when do I stop? When can I stop collecting data? Right? And sometimes you just say, well, if it's a ping pong benchmark, I can just do 1 million, and then I look at the data, and then I'm happy. But what if you run a single application on a large-scale supercomputer, and it takes you 12 hours to run it? You cannot just do 1 million, right? So you can do maybe 1, maybe 2, and this is rather problematic. So I recommend actually measuring until, again, this 95% confidence interval is within some distance from the median or the mean. Remember, if you do nonparametric statistics, you use the median. If you assume normality or any stronger assumption on the distribution, you can use the mean. In general, I would use the median as a more stable measure. But of course, this depends on exactly what you want to do. Okay, and this is a relatively straightforward technique. So you can basically implement a benchmark that keeps benchmarking until you get a statistically useful result. Or it tells you, look, I do not converge. Look at your distribution. It's probably crazy. Right? So one of these two things may happen. Okay. So, and then there are some tricks, but again, even sometimes for 3 to 4 measurements, you can get a tight CI. It's very, very interesting. But you must be very careful. And you have to assume normality, otherwise you need more. And also, if you run a Gordon Bell application, for example, what you can do is you can exploit the repetitive nature of these applications, and in the sense that they always do the same. There are kind of many of them are bulk synchronous, and you can just do statistics over the different rounds of this application. Right? So they will not run one big block typically. Okay. Good. Then a little bit more about experimental design. So now Garth is very happy because he discovered MPI, and MPI is always a very good source for performance studies. So you just measures, and this is something trivial that you probably all know, but for completeness again, if you just measure the number of processes and the completion time, if you just measure the powers of 2, then you will be in algorithm A. And but the problem is, as soon as let's say you measure powers of 2 plus 1, so in this case, 3, 5, 9, 17, and 65 here, you will get a completely different result because you use a completely different algorithm. Right? So many of us know this, some don't. This is extremely problematic, right, in practice, because most often people measure the nice case. So again, there's nothing to do against this, and this gets us to rule number 9, where you just have to document what you're doing. Right? This is extremely important. So we actually recommend vectorial design, which brings us back to the question that Christian raised. Vectorial design is extremely expensive because you look at all dimensions. You span your experimental space into a k-dimensional Cartesian space, and then you have to cover all the k times I, j, for j equals 0 to k combinations of the space. Right? This gets rather complicated and rather expensive. The only only useful thing you can do to capture this space unbiased is again random sampling of the space. Right? But then you have to do statistics on your sampling. You need to do two statistics on each measurement and on the sampling to make sure that you sample enough of the space to make a good, a reasonable statement about your system. Okay, but then a little bit more on timing in parallel systems, which is very surprising. At least for me, it was very surprising when I first realized this. So in fact, I can implement a benchmark that takes I can implement a broadcast that takes 1 point-to-point latency to complete. Of course, it's theoretically impossible, but I can implement and measure it. If I measure it like this, and this is in fact how most MPI collective measurements work. So what they do is they take the time, they run for I equals 0 to 1,000 times, and of course I plus plus here, and then they do MPI benchmark, MPI broadcast. And then they take the time again. So the broadcast I'm now implementing is very simple. Process 0 sends to process 1, then process 1 waits for process 0, then sends to 2, then sends to... It's a simple pipeline. But in fact, as we've seen some people realize, what will happen is that after process 0 sent the first message, it will send the second one, it will send the second one, even though it takes forever for these messages to get through all the processes, you will just measure the injection rate of the broadcast. Right? They will nicely align, and then if you think this is your latency, then you look pretty stupid. And in fact, many benchmarks work like this, right? Just check your average benchmark code, what they actually do. Okay, and then implement this broadcast. It's actually really funny. It works in practice, right? This is not an artificial example. Okay, so what you want to do here is you want to measure each operation separately. Okay, so now of course this guy is very clever. So now he implements his new reduce, and he comes up with takes 30 microseconds on 64 ranks. It's of course also nonsense for today's networks. So again, let's look at the data. So what you see here is now you measure each process separately, the latency of the operation, right? But the problem is, of course, and this is an MPI reduce, which means process 0 will take the longest time, and all the other processes may take very little time. So this is now a whole series of box plots, as you can see, right? And so we first see is a very high variation, okay? But now the question is, how did you summarize the data to get to these 30 microseconds? Did you take the slowest one, which is in fact 75 microseconds? Or did you just take the median or the mean or any useful statistical measure across these processes? Of course, if you do that, you can cheat again arbitrarily badly, right? And in fact, you can get back to this very result just by using statistics in the wrong way across the processes, right? Again, if you do this for parallel time measurements, you really need to report everything you're doing, and you need to report how you synchronize, and you need to report how you summarize the data. Pretty much none of the papers, including mine, right? So I'm not exempt from this, do this. Right? So basically, you don't know how the data was summarized, so you don't really know what the number means that you're looking at. The later ones of mine, we do this, but of course, when I started as a student, I didn't know all of these nice things. Okay, so the problem with this is I cannot give you a general rule how to summarize data. Right? The minimum maximum is something that's often used, so we just use the slowest process here, in this case, the 75. Problem is it's very unstable statistically seen. Right? Min-max is always unstable. The median or the average really depends on the use case. Sometimes you want it, sometimes you don't want it. The maximum is often a good one, but not always. Okay, so then the last, or the close to last one is, well, I keep reading these papers, and especially from domain sciences, that tell me, well, I compute some function in, I don't know, an hour. I say, okay, I have no idea what you're actually talking about. I have no idea what your function means. And for this, I just want to give you a little bit of an idea what you can do to give these numbers some meaning, right? So to give these measurement times some meaning. And this is a very, very simple idea. And the idea is really provide bounds. And so for example, if you have a code that runs on a single process at that time, you could just you could just plot the ideal linear speedup bound, which most of you do. Of course, after this talk, you will never plot speedup plots again, right? So you will plot time plots. I hope so. And then you have, of course, a lower bound to the ideal linear one. You can strengthen this lower bound, so you can make it closer to the actual measured function by applying Amdahl's law and removing the serial overheads, right? So because Amdahl's law will limit you a little bit, especially if you have initialization time, like in this case. And then you even can provide closer bounds, but this is again, it goes a little bit far. If you really like speedup plots, still you can of course do the same thing with the speedup plot, right? The linear bound, which is probably what many of you have seen. So let me just skip this. Very useful one is, by the way, this Amdahl's law bound, right? In these plots, it's very powerful. Okay, so if possible, show these performance bounds, upper and lower bounds, and you can actually establish a theory on these guys that I don't have time to talk about it. And in fact, if you establish a theory, you can prove optimality of your implementation, which is kind of a cool feature. Okay, so then the last one of these rules is really you want to plot as much information as possible. So, because pretty much always you can see all the problems if you look at the distribution of data. I mean, none of the problems really hides from you if you look at the complete data distribution. There are 3 very nice plots that I want you to know, where you can plot the distribution of the data. One is the, so basically, this plot plots pretty much all the points in your data set. And this is very nice. And so here, this is a box plot that I mentioned before. So here, the 4th quartile, the first quartile, the median. Sometimes you plot the mean, but again, the mean is not too useful in general. Especially the mean is not very useful if the upper part is different than the lower part, right? Because it's not a centrally adjusted distribution. This is again the data from the ping pong benchmark. Then there is a violin plot, which basically just plots the density distribution, of course, symmetrically in both directions, right? And of course also plots the mean and the median. And then you can plot, for whatever reason, you can plot both into the same diagram, right? If you really like to have all the data, because this gives you a lot of information, right? You have the first quartile, the 4th quartile, the mean, the median, the 95% confidence interval, and the full distribution all in one plot. Right? Of course, it's kind of messy to read, but this gives you most of the information of your data to interpret it statistically sound. So again, plot as much as needed to interpret the experimental results. And you can now, of course, say, well, that's extremely fuzzy. What does this mean is needed? Well, plot as much as you reasonably can, right? So this is what we are trying to do. Okay, so with this, I want to finish this short tutorial on how to measure and how to report data. But keep in mind always that performance may not be reproducible in most cases. And actually, I believe that in HPC, in other fields this is not the case, but in HPC, since we really run on these leadership class systems that are extremely hard to access for the average scientist, and even if I run today something on PitStein, next year you will never have the chance to find that system in that configuration again, because there will be a software update, right? Definitely. So, and you cannot reproduce many of the results. So keep this in mind. And this is why interpretability should really be the main focus of high performance computing reporting. And of course, you need to foster this. So you need to really understand how to do this. And I see these 12 rules as a start. So this really does not mean that they are complete or anything. But I think if you follow all these rules for every paper, that's a reasonable way to do this. We try to make it simple. So we have a library, liblsb, which you can use in your parallel codes that has an interface to R, the statistics language, and a bunch of R scripts that enable you to do everything we have I've shown in the last couple of minutes. So basically, you can use this liblsb to hook it right up into R, and then you can do all your data analysis in R, and there are example scripts and all of that stuff. So yeah, thank you very much. And if you have questions, I'm here.